Hey everyone, and welcome back to another Explainer. I am absolutely thrilled you're here today because, well, we're basically stepping into a time machine. We are heading back to the booming 1920s, a period of just massive, unprecedented expansion in the United States, to answer a question that sounds super simple but is actually incredibly complex. How did we start building the sky? Today we're going to explore the raw economics of that roaring building boom, and then we're going to funnel all the way down into the exact structural engineering that made it all happen. We're talking specifically about the ultimate showdown, the battle between load-bearing structures and framed structures. That is the true secret behind the modern skyscraper. All right, so here is how we're going to break this down. First up, Section 1, the roaring building boom. Then, Section 2, the economics of skyscrapers. From there, Section 3 is categorizing the concrete jungle, followed by Section 4, fighting the fire hazard, and finally, Section 5, bearing wall versus skeleton frame. Okay, Section 1, the roaring building boom, unprecedented scale. You know, right after World War I, the United States saw a construction expansion unlike anything the world had ever seen before. Entire cities were basically transforming overnight, but to really grasp the sheer magnitude of this shift, we have to look at the numbers. In 1927, the peak annual expenditure on all types of construction hit a staggering $14 billion. $14 billion. To put that into perspective, the entire national income that year was estimated at $74 billion. Think about that for a second. That means construction expenditures accounted for nearly 1/5 of the entire wealth generated by the nation. It was literally the backbone of the economy, second only to agriculture. And when you look at the data from the Department of Commerce tracking construction activity, you can clearly see this steady, massive climb straight through the 1920s. It's really interesting to note that new residential buildings were actually the engine driving all this prosperity. Of course, the numbers take a dramatic dip during the Depression years of the early 1930s, crashing down to about $4 billion. But man, during that boom, the sheer volume of building was truly historic. Now, you absolutely cannot spend $14 billion without an army of workers. The 1930 census gives us a really incredible snapshot of who was actually out there building this new world. We're talking nearly 1 million carpenters, over 400,000 painters, and hundreds of thousands of plumbers and masons. At the time, between 35% and 40% of the total cost of a building was purely for the labor performed right there at the site. It was just a massive, massive human endeavor. Moving right along to Section 2, the economics of skyscrapers, reaching for the clouds. So with all this capital flowing, developers didn't just build outward, they pushed upward. But here's the thing. Building to the clouds wasn't just an ego trip. It was pure economics. Before deciding how high to build, you have to look at costs. Using 1913 as a baseline of 100, the Engineering News Record Building Cost Index shows how wildly costs fluctuated back then, peaking in 1920, dropping, and then steadily climbing again. Because of these varying costs, engineers and architects had to calculate what they called the economic height. This is the exact number of stories that produces the maximum net return on an investment. For example, studies in 1930s showed that if your land in New York City costs, say, $100 to $300 per square foot, your optimal economic height was 63 stories. But if your land cost $400 a square foot, you had to build up to 75 stories just to maximize your return. The cost of the land literally dictated the sky. And this economic math sparked a timeline of towering achievements. For 15 solid years, the Woolworth Building held the crown at 792 feet. But then the race really heated up. In 1930, the Chrysler Building shattered the 1,000-foot mark. Just one single year later, the Empire State Building topped out at 85 stories, reaching 1,245 feet. But the engineers of the time, they knew they hadn't hit the ceiling yet. They actually calculated a theoretical limit of about 2,000 feet. The reason why, though, is absolutely mind-blowing. It wasn't because the steel would fail. No way. According to the structural texts from that era, the physical or engineering height limit was capped at about 2,000 feet because of the sheer physical weight of the elevator cables required for a building that tall. And, even wilder than that, the capacity of the average human eardrum. To service a building that high, elevators had to travel incredibly fast. We're talking exceeding 1,500 feet per minute. At that speed, the pressure changes and vibrations become a genuine, actual medical issue for passengers. It's fascinating, isn't it? Human biology was just as much of a limit as metallurgy. Section 3. Categorizing the concrete jungle, codes and safety. So, when you've got tens of thousands of people suspended high in the air, safety becomes paramount. Cities realized they had to step in. They used their governmental police power, which is the inherent power to protect public safety, to create incredibly strict building codes. Because that's the ultimate question, right? You have all these people, all this weight, hundreds of feet in the air. How do you regulate it? Well, before you can mandate how strong a building's bones need to be, you have to define what the building is actually doing. So, building codes first categorize structures by their use, or their occupancy. This makes total sense. A theater where hundreds of people congregate requires entirely different safety standards than a storage facility sheltering livestock, right? If you're building a hospital, institutional codes require vastly different floor loads and exit strategies than a residential apartment block. Which brings us to Section 4, fighting the fire hazard, the ultimate threat. Because honestly, here is a critical realization from the engineers of the time: gravity isn't your biggest enemy up there, fire is. The most important factor in classifying a building's construction type wasn't just what it was used for, it was its resistance to fire exposure. It's wild how precisely they measured this threat. Engineers literally tested how long a fire would rage based entirely on the exact weight of the furniture, flooring, and trim inside a room. The data is super clear. If a room has 10 pounds of combustible material per square foot, it will yield a destructive fire lasting about 1 hour. But if it's packed with 60 pounds of combustibles per square foot, like a really dense library or a packed storage room, that fire is going to burn with standard destructive intensity for 7.5 hours. So based on those brutal fire tests, the National Board of Fire Underwriters categorized all buildings into 5 distinct types. Right at the top is fireproof, where walls must withstand a 4-hour fire rating. And get this, steel columns must be encased in materials like concrete or hollow clay tile, because naked steel actually loses its strength super fast at high temperatures. Interestingly enough, heavy timber is ranked pretty high on this list. It's often called slow-burning construction, because thick, solid wood columns will char on the outside, but actually maintain their structural integrity for surprisingly long periods. But we always have to remember this chilling caveat from the engineering texts. Under severe conditions, no building is really fireproof. And now, the main event. Section 5, Bearing Wall vs. Skeleton Frame, the structural showdown. This is the absolute core engineering breakthrough of our explainer today. Because when it comes down to it, there are 2 fundamental ways to carry the immense weight of a building. First up, we have bearing wall construction. Picture a house of cards. The walls themselves have to do all the heavy lifting. They carry their own massive weight, plus the weight of the floors, the roofs, and everyone inside, straight down to the foundation. Now, this works totally fine for smaller buildings, but if you want to build high, it's a total disaster. To support 20 or 30 stories, the masonry walls at the base of the building would have to be incredibly thick, eating up all your expensive, rentable floor space. It was basically an engineering dead end for skyscrapers. But then came the total game changer: skeleton construction, or frame structures. Think of this using a human anatomy analogy. Instead of your outer skin holding you up, you have an internal, rigid skeleton doing all the hard work. In a building, this means rigidly connected steel or reinforced concrete beams, trusses, and columns transmit all the loads directly down to the foundations. So, to really drive this home, the crucial difference in this load-bearing versus frame structure showdown is this. In a load-bearing wall, the wall is the workhorse. But in a skeleton frame, the exterior walls are basically just a skin. They're merely supported at each floor level by the structural frame. They don't hold the building up at all. They just keep the wind and the rain out. This separation of the structure from the enclosure is the specific stroke of genius that allowed architects to build lighter walls, insert those massive windows, and shoot the Empire State Building 85 stories into the sky without the ground floor being totally consumed by solid, huge bricks. It's just an incredible leap in human ingenuity, right? We move from stacking bricks like blocks to weaving these intricate, fire-protected steel skeletons, capable of holding thousands of people up in the clouds. But it does leave us with this final, kind of wild thought. If the skeleton frame and high-speed elevator cables pushed us to the engineering limits of the 20th century, what new structural anatomy, what new bones and muscles will we invent to build the skylines of the future? Next time you walk past a towering skyscraper, take a moment to look past the glass and think about that brilliant, invisible skeleton keeping it all in the air. Thanks so much for learning with me today, and I'll catch you on the next explainer.